Greetings. Today we're going to talk about systems of differential equations. So we've been talking about linear systems where you have a vector x of t and the equation is x of t is a of t. The derivative of x of t is a times x. And we're going to focus now on the case when a is just a constant matrix. So this is constant coefficient systems of differential equations. So the equation is x of the derivative of x of t is a times x. And I'll just write that like this. X prime is equal to ax. And remember, x is a vector of functions of t, x1 through xn. And so this is really a system of n equations with constant coefficients. Well, let's start off really simple. Take the case n is equal to 1. Then you just have a single function of t, and the equation is x prime of t is equal to a x of t, and we all know how to solve that. X of t is c e to the at. Okay. Well, let's look at an almost equally simple example. Let's take n is equal to 2, and let's look at this equation. X prime is equal to 2, 3 times x, where the matrix is 2, 3 on the diagonal. So this is sometimes called the diagonal system. This is diagonal matrix, and this is called the diagonal system. And it's really easy to solve because it's not really a system in the following sense. If you write it out, x1 x is x1, x2, so it's the matrix equation is x1 prime, x2 prime is equal to this matrix times x1, x2, and so that's simply the pair of equations. X1 prime is equal to 2x1 and x2 prime is equal to 3x2, and x1 and x2 have nothing to do with each other, and so we know the solution is x1 is c1 e to the 2t, and x2 is a constant times e to the 3t. So in some sense this isn't really a system. In any event, but we want to write this as a vector, so we write it as, it looks like this, which we can think of as c1 times e to the 2t times the vector 1, 0, plus c2 e to the 3t times the vector 0, 1. So this is intended as a hint to what the general solution is going to look like. It has something to do with exponentials and vectors and such. I want to point out that this matrix, this vector 1, 0 here, satisfies the following property. If you take the matrix A, and A times 1, 0 is the matrix 2, 0, which is to say it's 2 times the original vector. The matrix A takes this vector to 2 times itself. And similarly, multiplication by the matrix A takes this vector 0, 1 to 0, 3, which is 3 times itself. So I'm going to write these two equations. A applied to V1 is 2 times V1, and A applied to V2 is 3 times V2. So this leads us to an extremely important definition. It's the following. You have a matrix A, a square matrix, n by n. And we say an eigenvector of A is a vector V, which satisfies the following equation. If you multiply on the left by A, what you get is a multiple of V. A applied to V is some multiple, which I'm calling lambda, times V. So in the previous page, that happened with x2 and 3. So lambda is called the eigenvalue, and the vector v is called an eigenvector. And you say that v is an eigenvector with eigenvalue lambda. So again, given a matrix, you look for a vector which is taken to a multiple of itself. And it's important that this vector is always non-zero. If you take the zero vector, this equation is always true, and that's kind of silly. So by definition, eigenvectors are always non-zero. Now, here's a key fact. Consider an equation x prime is equal to a times x, a differential equation with constant coefficients. Suppose v is an eigenvector with eigenvalue lambda. Well, then I claim you get a solution to this equation by taking e to the lambda t times that vector. Okay, e to the lambda t times the vector is a function, a vector of functions, and it satisfies the differential equation. And that's very easy to see, so let's just check it. Why is this true? Well, let's see. What am I saying? I'm claiming that x prime is equal to a times x. So I put a question mark here indicating this is what I want to check is true. So I'll compute the two sides and see if they really come out to be the same. So let's see. What is x prime? So x prime is the derivative of this vector valued function. So let's see. X of t is it's e to the lambda t times this vector v. So I'll write that out as e to the lambda t times c1 down to e to the lambda t times cn, whatever, where c1 through cn are the coordinates of v. So the derivative is, well, you do it one coordinate at a time, and in the first coordinate you pull down a lambda e to the lambda t c1, and in each coordinate you pull down a lambda. And so that's just, well, you can take all of those lambdas and just pull them out front, and you get lambda times, well, e to the lambda 1t c1, and so on and so forth, and you get exactly lambda e to the lambda t times v. Okay, so where does that leave us? I'm checking that x prime is supposed to be equal to a times x. And I just checked that x prime is lambda e to the lambda t v. And what is a applied to x? Well, a applied to x is a applied to e to the lambda t v. That's what x is. And e to the lambda t is just a scalar, so I can pull that out front. That's e to the lambda t times av. And av is lambda v. And then I can just change the order of the scalars back again, and I get e to the lambda t v. And there you have it. It's true. That's all it is. All there is to it. This explains why eigenvectors give you solutions of the equation. So let's do an example. Suppose A was this diagonal matrix. Well, that's exactly what I computed a couple of slides earlier. So just look back at that. Let's look at a more interesting example. Let's take A to be this matrix, 1's on the anti-diagonal. So let's see. A applied to 1, 1 is, let's see, it's 1, 1. So that says that the vector 1, 1 is an eigenvector, and A takes 1 minus 1 to, let's see, what does that do? It takes 1 minus 1 to minus 1, 1, which is minus 1 times itself. So I've just checked that these are two eigenvectors of this matrix with eigenvalues 1 and minus 1 respectively. Now, I'm not telling you how I found them. We'll talk about that later, but I'm just giving you an example of a matrix with two eigenvalues 1 and minus 1, and two eigenvectors, 1, 1, and 1, minus 1. Now, just a little bit of terminology. We refer to this pair consisting of the eigenvalue and the eigenvector as an eigenpair. So when you specify an eigenvector, you usually want to specify its eigenvalue at the same time, so it's really helpful to think of the pair consisting of a scalar and a vector. So in terms of the pair terminology, I have the pair 1 and the vector 1, 1, and that gives me a solution to the equation x of t is equal to e to the 1 times t times the vector 1, 1. That is to say e to the t times 1, 1. And I'll call that x1, and then I have another coming from the other pair. This is from the eigenpair minus 1 and the vector 1, minus 1. From this pair, I'm getting e to the minus t times the vector 1, minus 1. So that's two solutions to this equation, and it's a fundamental set of solutions that's easy to see. Therefore, the general solution to this equation is just a linear combination of them, c1 e to the t times this vector plus c2 e to the minus t times this other vector. Okay, so where does that leave us? Let's say we're trying to solve a differential equation. X prime is equal to ax, where A is a 2 by 2 constant matrix. Here's what you do. You find two eigenvectors, or excuse me, two eigenpairs, lambda 1, v1, and lambda 2, v2. And if you can do that, then the general solution is a linear combination of those two, c1 e to the lambda 1t v1 and plus c2 e to the lambda 2t v2. Now, does that really work? So there's really two questions here. The first one is, can you really do this? Can you always find two eigenvalues and two eigenvectors this way? These pairs. And, well, how do you go about that? And what if it doesn't work? What if you can't find two eigenpairs? Then what happens? So let's talk about that. Let's talk about how do you find eigenvalues and eigenvectors of matrices. Well, let's see. Here's the key result about this. Suppose I have an n by n matrix A. Then a number lambda is an eigenvalue of it exactly when the determinant of A minus lambda times the identity is 0. That is to say, you take the matrix A and you subtract off lambda from the diagonal entries, take the determinant of that gives you some equation, and you figure out which lambdas make that equal to 0. And I'm talking about, for this to be true, you need to allow complex vectors. So why is this true? I'm trying to find a vector such that AV is equal to lambda V. And I don't know what lambda is, but never mind that. If I had such a vector, that would be the same thing as saying AV minus lambda V is equal to 0. And now I have V on the left-hand side, so I can factor it out. The first term is AV, and the second term is minus lambda V. Well, let's see. In terms of matrices, that's lambda times the identity times v with a minus sign. So that's exactly the same thing as finding a vector such that a minus lambda I applied to it is 0. And remember, v is supposed to be non-zero. And an equation like this, a matrix times a vector is equal to 0, can only hold, if and only if, in fact, if the determinant of that matrix is 0. So that's the idea. Finding an eigenvalue is exactly the same thing as making this determinant equal to 0. So let's see. Suppose I find a lambda which makes it 0. How do I find the corresponding eigenvectors? Well, it's exactly this equation that I had on the previous slide. I just take a minus lambda times the identity, and I look for a vector which that kills, because then AV will be equal to lambda V. This is sometimes called the kernel or the null space of the matrix A minus lambda I. And the determinant being 0 is exactly what guarantees that it has a kernel or null space. So here's an algorithm for finding the eigenpairs. Now, everything I just said is for an n by n matrix, but now let's specialize to the 2 by 2. You look at this equation, determinant A minus lambda I is equal to 0. And you solve this for lambda. Okay. Now, given lambda, for each lambda, you know that there's a vector which satisfies this. That is to say, there is an eigenvector A for the eigenvalue lambda found by solving this equation. And then you have a little hope. You just hope that you found two vectors this way. That's what I said earlier, is you want to find two, and, well, we'll come back to that. Maybe you might not be able to. But assuming that you did, then you've solved the differential equation. The general solution is of this form. Okay, so let's talk about finding these lambdas. I'm trying to find lambdas which make A minus lambda I equal to 0, the determinant equal to 0. It's convenient to switch letters. Instead of lambda, let's use Z and make the following definition. If you're given a matrix A, an n by n matrix, the characteristic polynomial of A is the following. It's simply you take the determinant of A minus Z times the identity. If you write that out, that's a polynomial in Z, C0 plus C1Z plus C2Z squared and so on. If you compute the determinant, it's some expression like this, and it's written P sub A of Z. That's the characteristic polynomial. So let's do this example from earlier. PA of Z is, well, you take the matrix and you subtract Z from the diagonal, and you take the determinant and you get Z squared minus 1. And that factors as Z plus 1 times Z minus 1. So the two eigenvalues are 1 and minus 1. And that's what we found on an earlier slide. Now, here's an easy check. If you have a 2 by 2 matrix, there's a formula for its characteristic polynomial, which is Z squared minus the trace of the matrix times Z plus the determinant of the matrix. I'm sorry, I forgot a Z after the trace. That's, if you just write down a 2 by 2 matrix and compute it, you'll, if you know, A, B, C, D, if you just work it out, you'll see that you get that. And the trace is A plus D, and you know what the determinant is. That's AD minus BC. So, for example, let's find the eigenpairs for the following matrix. Let's take the matrix 1, 1, 4, minus 2. All right, well, let's see. The characteristic polynomial, according to this formula, is z squared minus the trace times z plus the determinant, which is minus 6. So that's z squared plus z minus 6. And you're interested in the roots of that, so you try and factor it. And let's see, it factors into z plus something and z minus something. How about z plus 3 and z minus 2? That looks good. Okay, so that's the characteristic polynomial, and therefore the eigenvalues are 2 and minus 3. And so now let's go find the corresponding eigenvectors. When lambda is equal to 2, you take the matrix A, and you subtract 2 from the diagonal. That is to say, A minus lambda I is the following matrix. 1 minus 2, 1, 4, minus 2, minus 2, which is to say, minus 1, 1, 4, minus 4. And we're doing a sanity check here. The determinant of this matrix should be 0. Which indeed it is. So if you write down this matrix and you don't get 0, you've made a mistake. And so we're trying to find a vector which is taken to 0, and that's just the equation minus x plus y is equal to 0. And then the second equation is redundant. It's 4x minus 4y is equal to 0. So it's really just one equation, x equals y, and so you can take x as y is equal to 1. And that's our 2 eigenvector, and I found that on an earlier slide. And similarly, when lambda is equal to minus 3, when you subtract that from the diagonal, let's see, what do you get? You get 1 minus minus 3 is 4, 1, 4, 1. And good, has determinant 0. And to solve this times xy is equal to 0 is just 4x plus y is equal to 0. So let's take y is equal to 4, and x is equal to minus 1. So the solution is, the eigenvector is minus 1, 4. All right, so let's see. Here are the eigenpairs. I found 2 and the vector 1, 1. And I also found minus 3 and the vector minus 1, 4. So therefore, the general solution is of the form C1 e to the 2t times the vector 1, 1 plus C2 e to the minus 3t times the vector minus 1, 4. And if you want, you can write that out as a single matrix, C1 e to the 2t minus C2 e to the minus 3t, C1 e to the 2t plus 4 C2 e to the minus 3t, like that. So that's from start to finish how you solve a 2x2 system when it has 2 distinct eigenvalues. So let's go back and look at the 2x2 case again. So you have this formula of z squared minus the trace plus the determinant. And I'm just going to write out z squared plus bz plus c for the moment, just to indicate that it's a quadratic formula, where b is minus the trace and c is the determinant. So all I'm saying is this is a quadratic function, and what are the solutions to it? Well, there are a couple of different cases. When you have a quadratic, it could be a product. It could have 2 distinct real roots, lambda 1 and lambda 2. That's sort of the nicest case. Another possibility is that it has a single repeated root, z minus lambda squared, And the third possibility is that it has a pair of complex roots. This should look very familiar to you all from some stuff earlier in the course. And that is to say it factors as z minus lambda times z minus lambda bar, where lambda is complex. So lambda is alpha plus I beta, and lambda bar is alpha minus I beta. Okay, so let's look at solving a system in the various cases. So the nicest case is case 1, where the characteristic polynomial has two distinct real roots, lambda 1 and lambda 2, and you find the corresponding eigenvectors. So you have two pairs, lambda 1 v1, lambda 2 v2, and then the general solution to the equation is simply c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2. And when you see a 2x2 system, you hope it's like that, because it's like this, because it's the simplest case. And the other cases aren't terrible, but anyway, this is the simplest one. All right, so what's another case? Well, let me skip case 2 and go directly to case 3 for the moment. So this is the case, it's really the next best case, where you have two complex roots. So PA of z having two complex roots, let's call them mu plus I nu and mu minus I nu. That's always the way they appear. And so as long as you don't mind working with complex numbers, you can get a perfectly good solution to the equation, just the same formula. It's e to the mu plus I nu times t times v1 plus e to the mu minus I nu times t times v2. And v1 and v2 are complex vectors, and c1 and c2 are complex numbers, and so on. And just like in the case of a second order equation, if you want the real solutions, what you should do is throw out the second guy and just take the real and imaginary parts of the first one. You take the real part of this function and the imaginary part of this function, and that gives you two solutions, and that's all you need. If I used the second equation with the c2, I'd also get two solutions, but they'd be linearly independent of the first two. It wouldn't be anything new. All right, so let's look at an example. Let's take A to be this matrix, 3 minus 2, 3 minus 1. So its characteristic polynomial is z squared, let's see, minus 2z plus 3. And let's see, what is that? The quadratic formula says 2 plus or minus the square root of minus 8, which is to say 2 plus or minus I times the square root of 8 all over 2. And the square root of 8 is the square root of 4 times 2. So you can factor out a 2 and get 2 plus or minus I radical 2 over 2, and that gives you 1 plus or minus I radical 2. So those are the two complex solutions, lambda 1 and lambda 2. Mu is equal to 1 and nu is equal to radical 2. Okay, so how do we find V1? Well, we take the original matrix and let's take the first eigenvalue 1 plus I radical 2 and subtract it from the diagonal. And let's work out what you get. You get, let's see, 2 minus 3, minus I radical, you get this matrix. And the last guy is minus 2 minus I radical 2. And we shouldn't have to check this, but just for sanity's check, let's compute the determinant of this matrix and see if it's really 0. Let's see, you get minus 4 minus 2, and then the signs cancel, so there's no I term, and plus 6, and yes, indeed, this number is 0. So that's good. So I'm trying to solve this equation. This thing times xy is equal to 0. Excuse me, is when I write that out, I get this. And I'm going to ignore the second row because it's linearly independent on the first and it doesn't matter. And so I'm trying to find x and y so that this holds. And there's two unknowns, so I'm free to take one of them to be whatever I want. And that gives me the other one. So let's take y is equal to, oh, that says y is equal to 2 minus I radical 2 over 2 times x. And just because I hate fractions, I'm going to take x is equal to 2. And y is then equal to 2 minus I radical 2. And it doesn't matter which, you can multiply it by a scalar, it won't make any difference. So my solution is e to the what? This is this complex number, 1 plus I radical 2t times this vector, which has an I in it, and I'll pull the e to the t out and expand the I part as cosine plus I sine as usual. And then it's times this vector 2 minus I radical 2. And as usual, this is a perfectly good complex solution to the equation. And there's another one coming from the other eigenvalue, but I'm going to ignore that. And I'm just going to take the real and imaginary parts of this guy. So how do I do that? Well, the e to the t part comes out, and you get e to the t cosine radical 2t. And then, let's see, that's real, so I have to take the real parts of this vector, which is 2, 2. And I also get a real part from the sine term as follows. So I have this e to the t, which comes out front, and then I have these terms with an I in them which cancel, and I get e to the t sine and 0 and radical 2. And that's the real part. So that's a perfectly good real solution. Now what's the imaginary part? Well, I get e to the t. Let's see, if I take the cosine and I multiply it by this minus I radical 2, that gives me something purely imaginary. So I put in 0 minus radical 2. And from the sine term, that already has an I. So from there, I'm going to get e to the t. And let's see, e to the t. And sine of this guy, and then just these real parts over here, 2, 2. So what I'm saying is that this expression on the second line of the slide is the real part plus I times the imaginary part. And now, as usual, like back in the business about higher order equations earlier, you do this trick. So then the general solution is, well, I'm just going to erase this word real here. I'm going to say it's C1 times this thing plus C2 times the other one, where C1 and C2 are real. So that's how you find the solution to an equation with complex eigenvalues. All right, well, let's see. There's one final case, which was labeled 2 earlier, and that's where the characteristic polynomial is just has a single root with multiplicity 2, but it doesn't have two linearly independent eigenvectors, but only one. So the algorithm that I just gave only produces one solution and not two. So let's look at an example. Let's take A to be this matrix. its characteristic polynomial is z squared, let's see, minus 6z plus 9 is z minus 3 squared. So there's only one eigenvalue, 3, and when you take a minus 3i, you get this matrix, and that only has one eigenvector up to scalar, the vector 1, 1. So the eigenpair is 3, 1, 1. And from that, I get a perfectly good solution. Well, there's no other linearly independent 3 eigenvector. So from this eigenpair, 3, 1, 1, I'm going to get a perfectly good solution. X of t is equal to, let's see, e to the 3t times the vector 1, 1. But what am I going to do for x2? Well, it turns out this is the one tricky part of all of this whole presentation, is in this case, what you do is you pick any other vector besides 1, 1. So, for example, just take 1, 0, as long as it's not a multiple of 1, 1, as long as it's not a 3 eigenvector. And then there's the following formula. You take e to the lambda t times that vector. Well, that doesn't work by itself because it's not an eigenvector, but then you take plus t e to the lambda t times a minus lambda I times w. So that's a little tricky, but it is what it is. And see page 10 in the notes for a little bit of more explanation of this. In any event, let's just write down what we get. It's e to the 3t times 1, 0 plus t e to the 3t times this matrix 1, minus 1, 1, minus 1 applied to 1, 0. And what you get is e to the 3t times 1, 0. That's the first term. And then there's a second term with a t, e to the 3t times, what is it, 1, 1. So this is similar to the repeated root case in the theory of second order equations, where you pull down this t, but there's an added complication having to do with this vector w. Okay, that takes care of the 3 cases, and I have one last thing I want to talk about, and that's the following. So I'm looking at this equation x prime is equal to ax, and I've told you how to find a fundamental set of solutions, at least in the 2 by 2 case, and in many higher order cases as well. Everything that I just said works, and you get this fundamental solution, which we were calling psi, and where you take x1 and x2 and make them the columns. And this is called the fundamental matrix. And then remember, there's also something called the natural fundamental matrix, where you modify this by multiplying on the right by the inverse. So let's do this in one of our examples from earlier. This is the example where A was this matrix 1, 4, 1, minus 2, and I found lambda was 2 or minus 3, and I had these two eigenpairs, 2, 1, 1, and minus 3, 1, minus 1, 4. And so the two fundamental solutions are e to the 2t 1, 1 and e to the minus 3t minus 1, 4. So this matrix psi is the matrix e to the 2t, e to the 2t in the first column, and minus e to the minus 3t, 4 e to the minus 3t in the second column. And that matrix psi satisfies the equation psi prime. Let's see, this satisfies psi prime is equal to A times psi. We've seen this earlier. It's just putting the two solutions into the columns. And in this case, this matrix phi is, well, you plug in t is equal to 0. So that psi of 0 gives you 1, 1, minus 1, 4. and you have to compute its inverse. Well, let's see, the determinant is 4 plus 1 is 5, so 1/5, and then this is the inverse. So phi of t is the following matrix. It's the original matrix, e to the 2t minus e to the 3t, so on and so forth, times this constant matrix on the right. And what you get is what? Let's see, you get 1/5, 4 e to the 2t, let's see, plus e to the minus 3t. And you also get a 1/5 e to the 2t minus e to the 3t, excuse me, minus 3t, and 1/5 4 e to the 2t, let's see, minus 4 e to the minus 3t, and then the last term is 1/5 e to the 2t plus 4 e to the minus 3t. That's the matrix capital phi. And that's also a solution to the equation, and it has the added bonus that when you plug in 0, you get the identity matrix. Okay, so we're almost done. I have one last thing to say about this. Let's consider this equation, psi prime is equal to a times psi. So that's just like the original equation, except I've written it psi as a matrix instead of a vector. And a is this matrix here. Well, let's forget everything I just said, and let's apply some wishful thinking here. Let's suppose that I gave you this matrix equation and I asked you to solve it without having said anything about eigenvalues and eigenvectors. Based on the case of where n is equal to 1, you might have a guess. So when n is equal to 1, this is just the equation y prime is equal to ay, and the solution is y is equal to e to the at. That's easy. So the wishful thinking is the following guess. Maybe the solution to this matrix equation is psi of t is equal to e to the a times t, where a is now a matrix, and this gives you a matrix function, a matrix valued function of t. This is, as I said, wishful thinking. It's not clear what this means exactly, but formally, just somehow, you know, applying wishful thinking, if you take the derivative of this thing, you just pull down the a. Psi prime is equal to a e to the at, and that's a psi. So that looks great. It's like the simplest thing I can think of. But the problem is, what on earth does e to the at mean? Well, by analogy with the exponential e to the t, it should just be this power series, e to the at plus 1/2 at squared plus 1/6 at cubed, and so on. It's a power series. So power series are problems. You got to worry about convergence and all sorts of things, but it's reasonable to think that something like this could work. So let's just continue with our wishful thinking and see how that would be. So if this was true, in order to solve this equation, you just need to compute this e to the at thing. So for example, when a is this matrix 1, -1, 1, 4, the formula is going to involve a and a squared and a cubed and so on. Infinitely many terms with all of these matrix products. There's no way to compute that. But here's the magic thing. E to the at is a solution to this equation. If call it psi, it's a solution to psi prime is equal to a psi, assuming that the details work out. And psi of 0 is the identity. Well, that's exactly what this capital phi did for us. Phi of t was a solution to this equation, satisfying phi of 0 is the identity. So, assuming I can make the details work, I've computed e to the at. It's this matrix, the solution to the equation. And I'm going to leave that here for now, and then the next thing to do is to talk about matrix exponentials and a completely different way of solving these equations involving matrix exponentials. But this was intended as motivation, and we'll see you next time.